So welcome back, dear students. Today we are going to start we are going to do the remaining part of design of a short column. We are going to see the design of short column. In the next semester you will see the design of long column. Here also we are going to see in specific the design of axially loaded short column. Okay, so you have the ultimate load carrying capacity. You will be having ultimate load carrying capacity, that is Pu is equal to FCC, that is the allowable stress in compression for concrete into area of concrete, that will give you the load taken by concrete, plus FSC, that is the allowable stress in steel under compression into ASC, that is the area of steel under compression. That is, you will get Pu is equal to FCC AC, that is you will be having both concrete as well as steel. So that will be taking the compression. The concrete FCC into AC and FSC into ASC will be taking the compression. And according to your FCC is what? FCC is the maximum compressive stress, that is 0.446 FCK. We have discussed this based on your stress strain curve for your concrete, and AC is the area of concrete, plus FSC. FSC is the maximum stress in steel under compression, that is 0.87 Fy for ms bars, 0.87 Fy ASC for ms bars. And if you are considering HYSD bars, it is 0.74 Fy. This is because when the concrete attains its maximum strain of 0.002, we have discussed in assumption of concrete. Assumption, you can see here in assumption the maximum strain, page number 70, the maximum compressive strain in concrete in axial compression is taken as 0.002. That is, when the concrete attains a maximum strain of 0.002, the HYSD bars won't attain its maximum stress value of 0.87 Fy. There it is limited to 0.74 Fy. That is, I can say here, the steel may develop full design strength in the case of ms bar when the concrete attains a limiting strain of 0.002. But for HYSD bars, the full design stress will not develop at a strain of 0.002. Hence, FSC is 0.74 for HYSD bars. Now, the IS code recommends the ultimate load carrying capacity of members by reducing the capacity by approximately 10% and thereby allowing a minimum eccentricity of 0.05 D. I told you the code tells you to use a minimum eccentricity of minimum eccentricity of E minimum, where E minimum is given by L by 500 plus B by 30. So whatever be, if you are telling that the column is axially loaded, but still there will be a minimum eccentricity. In order to account for that minimum eccentricity, the code says that we need to reduce this by a factor of 10%. That is, we will not use exact load carrying capacity of the column. We will reduce this value by, we will reduce this whole value by 10%. And in order to say that it is an axially loaded column, the minimum eccentricity should not be more than 0.05 D, thereby allowing a minimum eccentricity of 0.05 D. If it is more than 0.05 D, I cannot use this equation. That is, E minimum should not be more than 0.05 D. That is, then the column says that the column is an axially loaded column and there 10% reduction of the load should be made. It will be more clear when we are discussing a numerical. So here you have the equation Pu is equal to 0.446 FCK AC plus 0.87 Fy AC for ms bar, and Pu is equal to, that is the ultimate load carrying capacity, is equal to 0.446 FCK AC plus 0.74 Fy AC for HYSD bars. So in order to account for minimum eccentricity, we will reduce it by 10%. That is, I will use only 90% of this and 90% of this. So reducing it, or 90% of this, you will get this value as Pu is equal to 0.4 FCK AC and plus 0.78 Fy AAC for ms bars, and for HYSD bars you will get Pu is equal to 0.4 FCK AC plus 0.67 Fy AAC for HYSD bars. That is, we will get the ultimate load carrying capacity on a safer side. If I am taking, we will get the ultimate load carrying capacity as, if we are taking for a safer side, that is, we will take for HYSD bars for both ms bar and HYSD bar, we will be considering the safer side equation, that is Pu is equal to 0.4 FCK AC plus 0.67 Fy AAC. So this is the load carrying capacity of your column. Now, if the minimum eccentricity is more than 0.05 d, the section is designed for combined axial load and bending moment. That is, the condition for this was the eccentricity should be minimum eccentricity should be 0.05 d. If it exceeds this, we cannot use this equation because there will be bending also occurring in the section. That is, we cannot use this direct equation. This is only for axial compression. When there is bending also, we should design it in some other way. So I can summarize it like this. For using this formula, Pu is equal to 0.4 FCKAC plus 0.67 FOAAC, the following condition must be satisfied. First one, that is, the column should be a short column, because this equation is for short load carrying capacity of short column. Short column means your LEX by D and LEY by B must be less than or equal to 12. The next, that is, your LEX by D and LEY by B must be less than or equal to 12. Next one, the column should be subjected to axial load only. That is, it should not be subjected to any moments or transverse load. If that happens, it cannot be used. The E minimum should be less than 0.05 times the lateral dimension. So if these three conditions satisfies, then I can use this equation, and I can say this equation is specifically for short axially loaded column. This equation is specifically for short axially loaded column. This you can see in clause number 39.3, short axially loaded members in compression. The members shall be designed by considering the assumptions given in 39.1, that is your assumptions in limit state of collapse compression, and the minimum eccentricity. Minimum eccentricity is given in 25.4, that is your L by 500 plus B by 30. When the minimum eccentricity as given in 25.4, that is L by 500 plus B by 30, does not exceed 0.5 times the lateral dimension, that is, it does not exceed 0.05 the lateral dimension, then the beam may be designed by the following equation. That is what we have seen now. Pu is equal to 0.4 FCKAC plus 0.67 FYAC. Now I hope you have understood how this equation came, and this is applicable only for short axially loaded members where the E minimum does not exceed 0.05. Here Pu is the axial load on the member, FCK is the characteristic compressive strength, AC is the area of the concrete, Fy is the characteristic strength of compression reinforcement, and AAC is the area of longitudinal reinforcement for compression. So if you come here, this is the design equation for a short axially loaded member. So now we will see a question. A column of size 500 mm by 700 mm is subjected to a design to be designed for an axial load of 3600 kN using M25 concrete and Fe 415 steel. The unsupported length of the column is shown in figure. You can see here, this is having a column is having 500 mm by 700 mm. There is a beam B in x-axis and beam A in y-axis. So the unsupported length below beam A is given as 4.8 and below beam B is given as 4.1 meter. Design the column using limit state method. The column is held in position and restrained against rotation at both the ends. It's given the end condition, the column is held in position and restrained against rotation at both the ends, which means it is a fixed column. At both the ends there is no rotation as well as there is no translation moment. So it's given like this. It is 500 mm, 700 mm, beam A and beam B is given. So the unsupported length LOX is given as, OX means it is perpendicular to your x-axis, it is given as 4.8, and LOY it is given as 4.1. That is along the y direction. This is your y-axis, so it is given as 4.1 meter. You can see here. Beam A it is 4.8. Beam A, that is this one. X-axis it is parallel to x-axis. When bending takes place for beam A, it is going to take like this, place like this. That is along your x-axis, and beam B it is going to take along the y-axis. So you can say unsupported length LOX for x is 4.8 and LOY for y is 4.1. So the effective length LEX, you need to take it from page number 94. You will get this value. So if you take table number 28 from page number 94, table number 28, you will get effectively held in position and straight against rotation at both the ends. Then the recommended value, this is the theoretical value, and we should take the recommended value because we will not attain 100% fixity. So the recommended value is 0.65 L. The recommended value is 0.65 L. So your effective length LEX is 0.65 into unsupported length, that is 3.12 meter, and LEY is equal to 0.65 into 4.1, that is 2.665 meter. So the slenderness ratio limits LEX by lateral dimension. Here lateral dimension is 700. LEX by D is 4.46 and LEY by B, that is your lateral dimension, that is 5.33, which is less than 12. That is LEX by D and I specify LEX by D and LEY by B is less than 12. So I can call the column as a short column. This is a short column. Now we'll go for checking E minimum. E minimum, the unsupported length is different along both the axes. It is one is 4.8 and for Y is 4.1. So E minimum has to be checked for both the axes. About X axis, it is unsupported length divided by 500 plus D by 30, that is 4800 divided by 500 plus 700 divided by 30, or 20 mm, whichever is more. So about X axis E minimum, I will get it as 32.93 mm, and you will calculate 0.05 D, that is 35 mm, which means E minimum is less than 0.5 D. I can say that the column is axially loaded. The second one, about the y-axis, if I am taking LOY divided by 500 plus B by 30, here along the y-axis the lateral dimension is B, so I will get it as 24.866 or 20 mm, whichever is more, so I will take it as 20 mm. Now 0.05, that is 0.05 the lateral dimension, that is 0.05 into B is 0.05 into 500, that is 25 mm, which means E minimum is less than 0.05 D. I can say here E minimum XX is less than 0.05 D and E minimum YY is less than 0.05 D, which means the minimum eccentricity condition is okay. Both the axes it is less than 0.05 D, so then I can use the equation for finding the column is finding the axial load, and the column is subjected to axial load only. So the cases which the column is a short column and the column is subjected to axial load only, so that I can use this equation, that is PU is equal to 0.4 FCK AC plus 0.67 FY AAC. Here P is given as 3600 kilonewton because here the given value is your axial load which is acting. Here it is being acted upon by an axial load of 3600 kilonewton. So you need to factorize this load. So you will get this load as PU. In order to find PU, you need to factor it by 1.5. That is, you will get it as 5400 kilonewton. So applying this, I can write AC is equal to gross area minus area of steel, isn't it? The total area I will denote it by AG, that is your gross area, which is equal to 700 by 500 minus area of steel under compression will give you area of concrete, isn't it? Because when I am taking the cross section, gross area minus area of steel will be your area of concrete. So here the unknown value, the only unknown value here is what? ASC, because all the other values you know. So from here you will get the value for ASC as 7088 mm square. You will check for AST minimum, that is I have done that. AST minimum is 0.8% of cross sectional area, and AST maximum is, since here nothing is mentioned about the lap length, AST maximum you can take it as 6% of the cross sectional area. Do check for that. If it is satisfied, you can use this equation. So we will assume 28 mm diameter bars. So the number of bars required is equal to area, total area divided by area of one bar. You will get as 11.51. We will take it as 12. So use 12 numbers 28 mm 5 as your longitudinal or main reinforcement. Now the next one is design of lateral ties. So till there we have discussed how to find the longitudinal reinforcement. Now the design of lateral ties. the diameter of the lateral ties to be taken is either 5 main divided by 4. We had taken 5 main as 28 mm. That is 28 divided by 4, 7 mm, or 6 mm, whichever is more. So we will take 7 mm. But here we don't have 7 mm bars, so we will assume 8 mm bars for lateral ties. We will take 8 mm bars for lateral ties. So the spacing of the lateral ties should be either 500 mm or 16 times 5 main small or 300 mm. So this is 500 mm. We are using only one type of bar, so 16 into 28, which is definitely greater than 300 mm. So the smaller of this will be taken, that is 300 mm. So we will provide 8 mm 5 at 300 mm center to center as lateral ties. So we have provided 12 numbers of 28 mm 5 as longitudinal reinforcement and 8 numbers of 8 mm 5 at 300 mm center to center as transverse reinforcement. So you'll get the figure like this, that is 500 mm, 700 mm, and minimum cover of 40 mm is provided, and we will arrange it in this way as that this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You get 12 numbers, but we cannot arrange it like this because the distance between your lateral ties from here to here is definitely greater than 300 mm. So we will provide the lateral ties in this way, because otherwise what will happen is this reinforcement has a chance for buckling. So we will provide it in this way, that is we will provide cross ties also like this. Along the periphery we will provide the cross ties also like this. So this completes the design of a axially loaded column. We will discuss some more numerical in the next class. Thank you, students. Thank you and have a nice day.